have Sakura here telling us about categorical anomaly matching.
Okay, so thanks so much. Thanks, Matt, and all the other organizers for this fantastic program that you've been running for the last few months. And we've all benefited from this through talks, but also through speakers that have come to the UK, and also for giving me the opportunity to speak here about some work. But first of all, I was a little puzzled what I should talk about because the audience is really broad. And so it felt like I would have to speak in 3 different languages and still I would communicate 0. And so I actually settled on this particular topic because I think everyone somehow connects to, all the physicists will connect to the concept of anomalies, which I think is something that, even if you're a high-energy physicist or quantum matter physicist, you will appreciate that they're important. And the mathematicians might sort of be pulled in by the word categorical, so there's some math to this. But I'll try to sort of keep a balance in, how I go about it. So if there's some things that are unclear from your perspective, please shout. Anyway, so this is a paper that we wrote in August this year with my 3 fantastic collaborators, 2 postdocs, Andrea, who's sitting right there, Christian Copetti, who's on the job market this year, is amazing, and Johan Guy, who's my student, who's not yet on the job market, but you should keep an eye out for her. Okay, so this is about the following question, or the motivation is sort of coming from various sort of fundamental principles in physics. So Toft anomalies for global symmetries are really powerful tools. They constrain IR dynamics. RG flows are constrained in this way, and thereby the IR dynamics. But for example, they can tell you more concretely whether global symmetry can be gauged or not. They're an obstruction to gauging. They're a feature. They're not a bug. And more concretely, in the context of categorical symmetries, symmetric phases, and so on, they can constrain what type of phases you can get given a particular symmetry. And in more QFT language, they could, for example, constrain dualities, identification between theories, and the UV and IR. So this is an important thing. I don't think I need to motivate this further. And I also probably don't need to tell you that there's been these new types of symmetries that emerged in the last couple of years that are sort of the generalized type, in particular in high dimensions, and what mathematic categorical symmetries, starting with higher form, higher group, but then also higher categories. And so in physics lingo, these are these non-hierarchical symmetries. They don't compose like groups, but they're like they're everywhere. They're really, not just in one particular model, but they're in a huge class of models. They've been extremely well studied in 2 dimensions. Christoph and his collaborators in the past, of course, but in this sort of higher dimensional world, they've become very dominant in the last few years. These are global symmetries. We should learn how to address questions like Toft anomalies in that context. Right? So that's sort of basically the question. For such categorical symmetries, at the moment, or until this paper at least, we're lacking a sort of sharp way of quantifying what's an anomaly for such a categorical symmetry. So what's the anomaly data? Can we do RG flow matching of anomalies? But it's sort of a bit more richer than that because now we have all these high-dimensional theories, high-dimensional symmetries, and what happens when you have emergent symmetries that are now of this height? So higher form, higher fractionalization, etc. So the goal of this talk is to provide some characterization that's more quantitative when a categorical symmetry is first of all anomalous, that I think many people know the criterion, but to actually give a quantitative way of saying this is the anomalous part in your category, and that's the part you can't trivialize if you, say, for example, want a symmetric gap phase. And the tools are, from a math perspective, tensor functors. And I'll motivate from a sort of interface RG flow perspective why tensor functors are the correct sort of notion here. And alternatively, of course, because I'm giving the talk, this in TFT. So motivation starts with, you have a quantum system, and that's actually for most of this talk been 1 + 1 dimensions. I'll do at the end, if I have time, a higher dimensional example. the message will be, we can do this very concretely in 1 plus 1D, very systematically, and a lot of these things will lift to higher dimensions. So let's look at a fusion category, and since I don't know how much you really have seen this done sort of in a lot of detail, let me just focus on 1 plus 1D and I'll explain what we really mean by a fusion category symmetry. See, very briefly, not to bore the mathematicians, so we should think of this as topological line defects in a 1 plus 1D theory, labeled by a finite number of generators, simple objects. They compose in this way, where these are non-negative integers, and that means it's non-invertible generically, because this is a sum of generators, and so you don't get something like group-like composition. But very importantly, there is also this thing called the associator. So if you bracket like this, or you bracket like that, there's some kind of isomorphism, the associated isomorphism, and we might have heard this sort of calculate in various ways, but there's an important piece of datum that sort of lives at the junctions of these topological line defects. And then there are coherent relations if you now take multiple of these objects, you bracket them, and they have to satisfy certain additional consistency conditions. Okay, so that's what you should keep in mind. If you want, you can take the Ising fusion category as an example. But the question we're trying to answer is, you have a UV theory, your favorite UV model, it could be a lattice model, it could be a continuum QFT, an IR theory where it flows to, so you have a TUV and TIR connected by an RG flow, and associated to each of these, there is a symmetry category, CUV and CIR. And the question is, given this RG flow, what are the things that we can say about this map? What properties of this map do we know? And the first sort of sniff test is, well, this can't be an easy thing to answer because neither UV is contained in IR nor vice versa, because we can have symmetries that trivialize, you can have symmetries that can emerge in the IR, and then in higher dimensions, symmetries really play wild because they don't even stick to the form degree. So higher form symmetry or zero form symmetry can sort of be like matched with a higher form symmetry. So these are these fractionalization, transmutation phenomena. So this is not a simple question, but we'd like to ask what type of properties do we need to actually even say that there can be such a map between these two categories. And the motivation comes from interfaces. So this was introduced by Gallardo quite some time ago. But so we're motivating why we say it should be tensor functors by looking at the sort of system. And it's not that I'm going to describe to you these RG interfaces. I know there are lots of interface experts in the audience, but this is to motivate sort of how we think about the consistency conditions that a tensor functor satisfies coming from this more physical perspective. Okay, so we start with a theory, TUV, and then we play sort of a putative codimension one wall, and then on the other half space, we take the same UV theory, but now we add a relevant deformation. So now the question is, if I now follow this, I usually flow here to stay, I didn't do anything, but on this side I'll flow to some IR theory. If I now place the topological defect, so this is one of our symmetry generators into this, the question is, so what happens to this defect as I go along this RG flow? And so this D will just stick to D, but then D here maps to some F of D. And the question is, what are the properties of this map F such that this is sort of consistent with this RG flow? If you want to sort of have a concrete thing to think about, for groups, you're totally aware, say a finite group G, you have these D's are composing like group multiplication. There can be an anomaly, which is this 3 cocycle omega, value in H3 of G comma U1. And then we would say UV symmetry to an IR symmetry is sort of an okay map. It's a group homomorphism if we can pull back the IR anomaly through this map phi and get the UV anomaly. And so our question is, can we actually formulate this in a slightly more abstract way in terms of these defects so that we then actually extract the condition on what this map F is without having to rely on these kind of group theoretical notions.
Questions?
Yes? You're going to ask me about RG interfaces. Yes.
No, I just want to ask if at this point you are you're asking that O is uncharged under D.
That what?
That O, the operator by which you.
So I will get to this in a second. In fact, this picture here, there can be local operators, but they will just pass through. These are topological operators.
So, but the operator by which you're deforming on the right hand side has to be neutral under this symmetry.
There's no symmetry on I mean, no, I mean, absolutely. You're asking whether I'm actually, it can be charged. Absolutely.
And D stays topological on the right hand side if O is charged?
It will not be topological, right?
Okay.
But in general, of course
okay.
not. But I think in this paper, you could just look at any kind of deformations and ask this question. Anyway, so what I would like to do is now sort of look at what I could do with these topological things. There are junctions. For example, I can form up these three topological defects, and I can push these through. There's just a topological junction. I can pull it through this interface to the other side, and then do the RG flow here and the RG flow here. And so essentially, I get a junction here, which is sort of some vector space and multiplicity space, and a junction over here, and this could be now related by some linear map. So between this junction and that junction, between these new defects here, there could be sort of a linear map J of D1, D2, D3 that maps this vector space on the left-hand side to the one on the right-hand side. And now, of course, if I have additional defects and I look at the more complicated coherence relations, I'll get conditions on this here. And in fact, these exactly will be mirroring the conditions that a tensor functor in this context of the fusion category context would satisfy. So it's just basically a pictorial way of thinking. If you had such a system, you deform with this Rogan operator, you flow to some theory, what actually should we expect from this thing here, right? So this is essentially the setup we're asking. And here it seems to be saying you can have a map of the D, it should be some kind of map that of course respects some basic properties of this category, but then also these junctions actually should be mapping into each other in this sort of way by this linear map. Okay, so for so this is basically just to motivate the introduction that we would say now these things should be tensor categories. So what we'd like to have is under the RG flow, if I compose defects, so that's the symmetry structure, this should be somehow consistent with this composition structure, the anomaly data in some sense, but also with this RG interface picture. And so our proposal is that F should be a tensor functor, which essentially means it's a structure that if you act first on the tensor product, there should be some isomorphism, some natural map on this category that then maps it to the product of the f of d, f of the long D2. And in addition, there'll be these sort of, this is this functor here, and this is this natural isomorphism. Yes?
Sorry, could you go back to the previous slide?
Yes?
A tensor functor has an isomorphism.
Yes,
There
here.
are notions where this is not an isomorphism.
There are notions. No, I would like it to be an isomorphism.
Why?
Because I actually want this, right? So if it's not an isomorphism, then it means on simple object, right? If I have fusion here and a fusion there, I should actually have a map between these two composites. I don't want the fusion to somehow change. I think that would be the case if it's not an isomorphism, no?
Yes, but there are interesting functors where you have maps in the two directions and they are
okay.
not each other's inverse.
Okay.
But let's discuss this.
Yes, we can, yeah, yes. Very good. So this is basically just this compatibility with the tensor structure. And then we had seen in the RG flow picture that there could also be these maps on the junctions, and that is essentially some kind of mathematical reformulation that there's this natural isomorphism satisfying some additional consistency conditions with cocycles in these categories. Anyway, this is just to say we would like this notion of tensor functors not to just pop out of nowhere. It's actually extremely natural from this perspective of these RG interfaces. Anyway, so what we would like to do is not just have a map, but actually say, well, given a symmetry, can I say, first of all, can I materialize it? So can it in the IR, so is it anomaly free? But also if it's not anomaly free, what's the anomaly? So this is the question about how do I quantify what the anomaly is. And of course, it's well known that symmetry is anomaly free if it has a so-called fiber functor for the condensed matter people, if it can be sort of, you have a trivial gap phase, symmetric gap phase, you have a trivial vacuum or an SPT, so you have a functor from the category to Beck, and that precisely has to be a tensor functor. And so this is a nice criterion to say yes, no, anomalous or not anomalous, but, or not anomalous, anomalous, but the question is sort of, if this is not the case, this doesn't exist, how do you actually say what the anomaly is? Just like you say there's a co-cycle in the group-like situation. And so this is what we are doing in this paper, and one way is to formulate in terms of the functors, but also then in terms of SymTFT. So let me just summarize the upshot, and then we will work through a few examples, and I'll motivate it then through the SymTFT, where I hope it's a little bit more intuitive also for the physicist. So our proposal is what we can look at now, sort of the analogs of short exact sequences for groups, but now for tensor functors. So you have, this is our symmetry category, say, and there can be a tensor functor from another category n, and that's an injective functor. I will not define all the details of injective and surjective functors, so P is a surjective functor. This is a short exact sequence in the sense that the image of I is the kernel of P. There are various additional conditions one needs to supply here, but essentially I'll sort of assume that all our functors are normal, and then I'll define this thing n to be actually a normal subcategory. I can embed this into this, and then I project onto S. Now we said if a category has a tensor functor, it has a tensor functor 2 Beck, then it's anomaly free. Well, n, I can compose, and I go to, because of this condition of exactness, n in fact is anomaly free, right? Because I can just go all the way here and Hill maps to Beck. So this is, in a way, you should think of this as an anomaly free part of the symmetry. It's a way of thinking about any n that fits into such a sequence will be an anomaly-free part of the symmetry. Now, the condition that you have such a tensor functor isn't just saying that there is some subcategory that looks like it's sort of, doesn't have an anomaly on it. It really has to be a normal subcategory in this sense. It fits into such a sequence. One example is, for example, the easing. It looks like there's a Z2, but actually that doesn't fit into such a sequence. Okay, so now if C does not admit any non-trivial such normal subcategories, so basically you can find such a thing that it fits into such a sequence for a category C, then there's nothing that's anomaly free, essentially. So what you basically have is then sort of like an anomalous building block. And we call these things anomalous simple categories or ASCIIs. So they're like the building blocks for the anomalies of categories. Examples are just Beck Z2 omega, so Z2 with an omega non-trivial anomaly. But also, as I was just saying, the easing one is also an example of Fibonacci, Hager-Rupp, you name it. So there are many such irreducible.
Is there a weaker sense in which Fibonacci is anomaly free? Like you can gauge, sort of, you can build an algebra object out of Fibonacci and gauge it.
So this is like, if you're saying Fibonacci is anomaly free, then you would claim that there's a trivially gap phase.
Yeah, so I agree there's no trivially gap phase.
Right?
Maybe in a sort of.
But there's also no subcategory.
Yeah,
obviously.
just in a weaker sense. Like if you take 1 plus tau, you can build an algebra.
Oh yeah, you can do the
Or trivial. Maybe that's the.
Yes, but why is that a good criterion? Because there is no.
I don't know. People just, I guess, for groups, right? People talk about this fiber functor and the gaugeability as being the same thing, right?
That's
right.
Right.
There's a bifurcation, right, in the case of non-invertible symmetries. Right?
But I would still want to say a symmetry that I can't trivially gap is anomalous. No, I thought
that's
we should. I think we should agree that this fiber functor statement wherever it was. That is a way of saying At least that answers the yes/no question.
Yeah, it's a good
Right,
definition. I'm
and-
saying you could have another definition for non-invertible symmetries. Maybe it's not a good one for
Because I don't think you have a trivial gap phase.
yeah, for Fibonacci.
So then I would like that to be the criterion,
Okay.
right? Because that's also for the groups. It just takes the definition for groups. If you have a Z2 with an anomaly, there's no trivial gap phase. Right? So in that same sense,
It generalizes, sure.
it generalizes that. Okay, so, all right, so these ASCIIs you should think of as category C, where there's no anomaly-free subcategory. So they're like these anomalous sort of like building blocks. And what we'd like to now do is, say you have a given symmetry C, you take your favorite symmetry category, like for example in Matt's case Fibonacci, then you ask, find all these NIs that fit into such a sequence, so all the normal subcategories, and look at all these sequences. Then you should think of these things over here as essentially these anomalous building blocks. So and for Fibonacci, in that case, there's no n, so in fact, it's its own ASCII. So it's like an irreducible building block for the anomaly. But generically, and I'll give lots of examples, these form sort of the building blocks of the anomaly for the category C. So you take these sequence, it's literally like, maybe I should do the group example, and I'll do that in a second. But anyway, so just to sharpen the statement, you have a CUV. What are possible IR symmetries that you could get from this perspective is essentially you look at all these sequences here, you look at all the maximal NIs, right? So the maximum in the sense of there's no other normal subcategory where it sits inside that also has an injective functor to your symmetry category. And then this collection of SIs that are the projections, those form these anomalous building blocks for your symmetry category. And those you can trivialize in the IR. Yes?
For the example of Ising, why is the Z2 subcategory not normally?
Yeah, so it's not actually a tensor functor. It really has to satisfy all of these conditions of tensor functor, and this one, there's no Z2 back Z2 that embeds as a tensor functor into that. Yeah, I'll actually look at other TYs in a moment also as well. But so it's misleading to think it's just a subcategory. Subcategory is not enough. It really needs to have the structure of these tensor functors, the compatibilities with all the associators and everything. Once you check that, this is not the case. And in the Ising case, for me, the simplest way to see it is just to look at it in the SimTFT, and I'll get to that, and then we can talk about it again. Okay, let's look at groups and just reformulate what we just discussed in terms of things we know. We have a group with a normal subgroup N, and let's say there's an anomaly, omega GU1 in your group summary, so I will denote the category just in terms of the standard notation vec G omega, so these are just G-graded vector spaces, but now there's an associator, omega value in this group homology at H3 of GU1. Then such a short exact sequence of groups will translate to a tensor functor short exact sequence. This is the vec of the normal subgroup, and this is the projection. If this cocycle, this anomaly here, is such that we can pull it back and get the one on omega. And that's sort of this condition that you know from anomalies of group symmetries. And now you're actually asking sort of, what is now the anomaly-free part? Well, vec N is the anomaly-free part, and this is the anomalous part. And if you pick this sort of large, the largest, sorry? Question? Later. Okay, good. So anyway, let's look at this for Z8 with anomaly 4. So this is a Z8 choice of cocycles. Let's take omega equals to 4, and that's Z8. And then in fact, one can look at Z2 subgroups. And there are now two such short exact sequences. So first of all, you can embed Z2 into Z8, and you project onto Z4, but it also needs to be compatible with this anomaly. And there are, in fact, two choices of this anomaly on this right-hand side, on this projection. And both of them pull back correctly through these maps. And so you would now say this symmetry, so the Z8 group symmetry with anomaly 4, has two ways. You could have two types of ways to go into IR where you have either this symmetry or that symmetry. And in this terminology that we now have introduced, this is saying that the ASCIIs for the symmetry are these vec Z41 or vec Z43. 3 is the same as -1. Okay, so basically this is sort of a way of seeing how we think of these type of short exact sequences of tensor categories in this group context. But of course that's boring, yes?
Is the largest normal subcategory unique? In general, not in this example.
I don't think so. I think there were, no, it's not. But I think it's hard to find examples, but I don't think it's unique. But that's fine, right? It just means you can trivialize different parts of your symmetry. And there's always, then it's just saying, as you flow to the IR, certain parts of this become trivial, and then you're left with this sort of, I always think of this as the nucleus of that's the part you can't trivialize. So it's just sort of giving you, given a category, you pick these Nmax that fit in a sequence, it outputs these anomalous ASCIIs, and that's the data that you can sort of now should be able to see in the IR. So, but no one asked me how you come up with these sequences. This is not super straightforward, and to me, you know, it's a natural question to ask, can you now recast it in terms of a SimTFT picture? It's also nice to do that because everything I said so far is for fusion categories, and if you want to extend it to higher fusion categories, there isn't enough sort of mathematics, to my knowledge, about fusion 2 categories, 3 category tensor functors. So in fact, it's useful to have a different way to approach it from a physics perspective. So that's how we will now introduce the same concepts in the SimTFT. So the SimTFT, you heard talks about this, but yesterday there was talk, so I don't think I need to introduce too many things about it, but just the basics. You have this quantum theory that now became math frac T, so it's the same as the Kelty, with some finite symmetry D, some fusion higher category if you want in the dimensions, then the SimTFT is D plus 1 dimensional TQFT that's obtained by gauging the symmetry into D plus 1 dimensions. So for group symmetry, it's just a Dicke-Witten theory. For the group G, for the finite group G, for continuous symmetries, you saw this yesterday. I put the sandwich, I rotated it by 90 degrees. You'll see in a moment why. So here's our symmetry boundary, here's our physical boundary, and then I'm here looking at sort of, this should be really different color. This is really a topological defect that now can end on both of these, and we collapse this sandwich now along the y-axis to this one-dimensional line here schematically, and then this topological defect becomes a charge under that symmetry. So that's how you sort of encode generalized charges in this picture. We're not too much interested in the actual topological field theory, but what we're interested in is in the Drinfeld center. Those are the defects of this TQFT. And in 3 plus 1D, these are just anyons, so these are topological lines. And now the symmetry boundary is given in terms of sort of a gap boundary condition, or so-called Lagrangian algebra in this Drinfeld center. And there's always one gap boundary condition that's essentially the one that realizes the original symmetry, and I'll call that the Dirichlet boundary condition. And then the physical boundary condition, which we won't be too fussed about today, is encoding all the physical degrees of freedom, the dynamics, and so on. Okay, but now we are interested in UV IR, so I actually need to now look at a slightly more complicated picture, which goes by the name of a club sandwich. So we now have 2 topological field theories. One is the center of C, and then there can be an interface now. And this is sort of some reduced topological order, if you wish, where, for example, I've partially condensed some of the topological defects. There's a symmetry boundary here in the front. On one side, a symmetry boundary on the right-hand side, and then on the physical boundary in the back. And what we really want is, right, we're not too interested in just a generic setup, but what I'd like you to sort of think about is here, we'd like to ask the question, given a UE SimTFT with a particular symmetry boundary, and an IR sim TFT with a particular symmetry boundary, what kind of interfaces are there, and in fact what pairs are compatible, and which of these type of setups actually correspond to these tensor functors. So if you want to go back to thinking about RG interfaces, you collapse along this direction, you squeeze it to sandwich like this, and then you have your TUV, your TIR, and your RG interface. But what I'm interested in is the symmetry aspect. I'm actually going to collapse it like this here, and then I get, this is the sim TFT for the symmetry in the UV, this is the sim TFT of the symmetry in the IR, and then there's this interface between them, a topological interface, that's not the same as this one here, please, and then there's some physical boundaries. And because I'm only interested in symmetries, I will take the top layer of the bread off and make it a quiche. So it's a club quiche because it's a club sandwich where I've taken off the bread. There's a very profound logic in this field, introduced by Greg Moore, I believe. So anyway, it's not my fault. So essentially what we have is these two TQFTs with an interface within each other, and now we know these symmetry boundaries encode the UV and the IR symmetries, and our claim was there should be a tensor functor between these two symmetry categories. What is that in terms of conditions on this interface? And what we showed in the paper is basically there is a sort of precise way of mapping this tensor functor properties to the sim TFT. And it just says that very impressionistically it means you take the UV symmetry boundary here, you fold over the IR, this interface, and that should basically rise to the IR symmetry. I have sort of a slightly more detailed description in terms of Lagrange algebra.
Is there like a pithy way to sort of describe? So I guess like to go between ZCUV and ZCIR, as you say, there's a topological, gap domain wall between them, and so I guess there's some kind of gauging on
The
general.
condensation of anion, but it doesn't have to. One way or the other way, but not all of it. All interfaces are necessarily given by anion condensation.
Sure. I guess that's my question. So let's say we're in 2 plus 1D. I guess in general, will be given by some kind of combination of 0 form and 1 form.
Yeah, but even in 2 plus 1D, you could say there could be, it's just some topological interface. Right? And I'm asking, given these two symmetry categories, and I want a tensor functor, what type of things, what's the equivalent condition on these? And it just is this condition.
So I guess like in general, you could say that there is some kind of gauging. It's not in general just 1 form gauging, possibly 0 form, possibly some higher structure that you're gauging that combines them.
Yeah.
But is there some pithy way to describe like the subset of these gap domain walls that correspond to RG interfaces? Like, so you're saying it's not just 1 form symmetry?
This is not the RG interface.
No, but it's the holographic or whatever. It's the bulk thing that the RG interface.
Yes, that's right. It's a collapse of this with that is the RG interface. Yes.
Yeah, I'm just wondering if this interface here.
But here I'm not even including the physical boundary, right? So this is not even asking about a particular RG. You could do that if you then also close it up, and then you go back to this picture here where you've now actually got this RG interface, right? But you need to specify a physical boundary. So here I'm just asking, in terms of the symmetries, we said I have a category that lives here, a category that lives here. Topological lines are confined on these two boundaries. What is the statement that's equivalent to saying that there is a tensor functor? I'm going to just tell this is this statement here, and you can formulate it again in terms of the anions in a 2 plus 1D system. That there's a Lagrangian here, Lagrangian there, and there are certain relations between the coefficient of the Lagrangian algebras that have to be satisfied. I won't actually do that because I don't think I have. So this is just one way of thinking about it is you can fold this over, get a doubled system with now gap boundary condition, and now any gap boundary condition of this folded theory is an admissible interface. And some of them will come from anion condensation. But it's a topological interface, so then if you really want to get your RG interface, you have to close up the top. Yes? You seem not...
Yeah, well, we can talk about it after. Yeah,
I mean,
I understand
yeah, you have to, right? I mean, this is just a quiche. You have just the symmetry boundary with a bulk attached. And because I'm just asking at the moment symmetry questions, I don't need to be concerned with adding that additional top layer.
Yeah.
You can do it, but it's not something that I'll discuss here. Okay, so as I was just saying, you can think of this as a gap boundary condition for this folded thing. Some of these will come from condensing algebras, either from here to here or from here to here, depending what the relation between the UV and the IR symmetries are. And either way, what this folded picture does is it gives a map from the center of the UV to the center of the IR. And so it maps an anion to a collection of anions. Some of the anions will be confined, and so now you can formulate in terms of these coefficients here, the condition if you have two Lagrangian algebras that are giving you the UV and IR symmetries, these coefficients here, then this map here is just a nice linear relation. And that's sort of a much simpler thing to check if you're already working with Lagrangian algebras most of the time anyway. Okay, anyway, so the message is we have a condition that translates tensor functor to a very concrete condition on interfaces in the SimTFT. And now the question is sort of, well, we're not just interested in any kind of tensor functors, we're interested in particularly these short exact sequences of tensor functors that will give us these anomaly-free subcategories and the ASCIIs. So we need to now define what does it mean to be injective and surjective in the context of the SimTFT. So tensor functor is injective. In physics terms, if this UV symmetry X facial in the IR, then basically this interface has to be of the following making. So here I'm thinking of each of these boundaries given by some Lagrangian algebra, as I wrote in the earlier slide here, and that means that there's an algebra inside the center of CIR such that this algebra here is contained, so any anion that is in this algebra, any anion that actually ends on this interface also is in the symmetry algebra of the IR symmetry. So it's an electric subalgebra of the IR. So that's the condition in the SimTFT for the injectivity. And now the surjectivity is basically, this interface corresponds to a surjective functor. It basically, there's an algebra, so any anion here ends here, that's in the algebra, now in the CUV. But the only one that's shared with the UV symmetry is 1. Then this is a surjective tensor functor. And now we can combine it and get these short exact sequences. So now this is our symmetry category C. This is this thing here in the middle. We have two interfaces, one I and P, here and here. And then we want this one to be injective and this one to be surjective. So we have basically conditions on these interfaces that are related to the Lagrangian algebra of the symmetry boundary that we started with. And so now this kind of picture basically becomes a short exact sequence if in fact the composition, right, is trivial, and that means that in fact the product of these two algebras gives a Lagrangian algebra, and so essentially you can just sort of squeeze this and decouple these two things, and you get sort of a gap boundary condition instead. So that's a way of recasting now all the conditions of short exact sequences and tensor functors in terms of the SimTFT. I know this is a bit quick, but I want to actually show you how we can now study some interesting examples before I run out of time. So, so what we want to do is now reformulate this whole ASCII story in terms of the SimTFT. Let's go back to our group example. Remember this example with Z8 with anomaly 4. Now we can sort of say what's the SimTFT for these abelian groups with anomaly omega. Well, they have, the omega is the cocycle. I can write it explicitly in terms of some formulas for these abelian groups. So just some phase that's determined in terms of which anions you put in there. And then the SimTFT is just a Dicot-Witten theory for Zn and 2 + 1 dimensions with twist omega. And the anions are just some powers of E, some powers of M, and they're mutually non-local. And each one of these has a spin that's now sort of modified by some additional, depending on this cocycle. And there's also this sort of identification on these integers of these powers here. And there's always this canonical boundary condition, which is just the sum of the electric power of electric anions. That gives the group symmetry Zn with omega. Okay, so for Z8, we said we're just running now through the same sort of arguments as in the tensor functor short exact sequence. There's the canonical Dirichlet boundary condition, which is just the sum of all the electric anions. So this is the one I'm putting here. And then we'd like to now actually look at these two interfaces. They're given in this case by condensing anions. In this case, to go to Z2, I basically have to just condense sort of the even powers, and then I get a remnant Z2. It's basically condensation this way. And that's an electric algebra, obviously. It sits inside the symmetry algebra. And then the magnetic algebra that basically needs to have distinct. The only joint anion with this is 1, and there are 2 algebras of this type in this case, and they give 2 different condensations to the SimTFTs of Z4 with 1 and Z4 with omega equals 1. And those are precisely the 2 tensor functors we saw earlier. So here you can just do an exercise in linear algebra and get this SimTFT picture, and it again says you can, in this symmetry Z8 with omega 4, you can trivialize a Z2, and then there are 2 ways you can do that, and you get these 2 symmetries Z4 with omega 4.
It just makes sense. So here you to go from blue to gray, you do a condensation, an anion condensation.
Yeah, you condense this way, and here you condense
that way. Okay, so right.
Yeah, so this was this thing that these algebras, right here. This one was the algebra that had to have this algebra had to be an electric algebra, and this one had to be a magnetic algebra. That is this basically the only joint anion is 1, so it's sort of basically that's the surjective functor and this the injective functor, the analog of that. But each one of these 2 is a condensation, right? So the center of N is the center of C modulo that algebra, and here the center of S is the center of C modulo this algebra AP. Right, you go this way. Okay, but so far we have not done anything different from what you know, just build a lot of formalism. So now let's apply this to non-invariable symmetries, because that's when this whole thing becomes interesting and when we actually learn something new. So the simplest series of non-invariable symmetries you can think of are the covariant dummies with there's some abelian group A. There are also bicharacters for being the Schur indicators, which I'm putting on the carpet, except here specify the plus. But anyway, I will not give you the details. You can find them in the paper. I just want to illustrate to you what we actually, once we apply this to a now much more complicated non-invariable symmetry, what type of anomaly constraints we get. So these are just the generalizations of Kramers-Wanier. So TYZ2 is the easy inclusion category. So it has n squared is 1 plus A, where A is generative Z2. And there are now, for example, for all cyclic groups, for example, Z4, you just get n squared is 1 plus the sum of all the abelian anions. And so Z4 is this here. And now the SimTFT for that is known, and we can now study all the gap boundary conditions. They're also largely known explicitly, and then study these type of algebras. And in the case of TYZ4, we find there's one Z2 way, so there's again a Z2 that's anomaly free, and that's maximal. There's no Z4 that's anomaly free. It looks like there should be a Z4 subcategory, but there is no a normal subcategory that is Z4. So the maximal thing is Z2. This goes injectively into, you can inject that in TYZ4. And then there are again 2 ways you condense to, you can hardly see this. This is let me actually go to the next slide. There's one condensation to rect Z4 with omega 1 and one with Z2 with a mixed anomaly. And so this says if you have a TYZ4 category, it's a non-invariable symmetry, in the IR, you could trivialize a Z2, and you can do it in 2 ways. You can either go to Z4 with anomaly 1, or Z2 with a mixed anomaly. And so you could, these two are these ASCIIs, so these are these anomalous building blocks of your symmetry, and so whenever you go to the IR, you will not find a trivially gapped phase, but you need to find, if you say trivialize the Z2, you should actually find something that's consistent with these two symmetries. And of course, you then want to actually see that in action, so you can look at all the gap phases for Ty Z4. There are 3 gap phases, and each blue dot is, each blue and red dot is basically a vacuum. So this is a fully SSB phase, and these are partially SSB phases, where in particular here there's a Z2 that's preserved. And now you can ask, what are actually the phases? If you have a Z2 that's sort of trivialized here, that should be compatible with the 2 ASCIIs that we wrote down here, right? And now what are the gap phases for these guys? Well, those are also easy to determine. There's 1 gap phase is 4 vacua. In this case, there are 3 gap phases with these vacua, where these arrows are the 2 Z2s. And here, actually, the non-invertible guy was, by the way, the red one, and the black one is the invertible guy. So you see, these 2 phases are precisely compatible with the phases of this, these ASCIIs. So this type of structure, if you trivialize the Z2, is completely symmetry enforced, because that's the basic remnant anomalous part of the symmetry that then dictates what you need to be doing in terms of the symmetry action in the vacuum in the gap phase. Okay, so that's just to illustrate that you can actually really get information about which parts of your sort of gap phase story comes from now the symmetry that is anomalous, or the anomalous subsymmetry of your system. Okay, and we did this also for the other TYs. You can do it for all kinds of other symmetries, but the idea is relatively straightforward. You can now always write down the SymTFT, study these algebras, and that gives you all the ways you can trivialize non-anomalous parts and get information about the stuff that's anomalous. Okay, so I promised you there is some high-dimensional extension. That's why the SymTFT is sort of a good way to proceed. I think for Fusion 2 categories, there are some notions of tensor functors, but then you want an ejective, a surjective, a normal tensor functor. These concepts are, I think, not fully understood. So it's nice to also then go to maybe 3 dimensions, 4 dimensions, and in the SymTFT you can do that. It may not be very, very general and super, super rigorous, but there's a way of sort of applying that and getting interesting information about anomaly matching. So the one example I want to discuss, which is non-trivial, it's known in some dyes, which is coming from this Wang-Van-Witten kind of setup, is you can have in the UV a zero form symmetry in d dimensions with an anomaly. And then in the IR, you go to actually zero form symmetry with the same underlying group. That's not anomalous, but you actually have dual d-2 form symmetries, or higher form symmetry with some group, abelian group K, that has a mixed anomaly with the zero form symmetry. So you should be able to, in this formalism, say there's a consistent way to go from this to that. And in the SymTFT, it's a nice way to actually see. These are again sort of Dyker-Witten theories, 9 high dimensions for these groups G. The higher form symmetries, these are abelian, so they're again very explicit BF theories that we can write down, and we can study these type of interfaces. So the way to construct this kind of thing is to actually look at group G tilde. That's actually a group extension between your UV symmetry group G and an abelian, a central extension with K, and that's sort of characterized by this group cohomology class. And now you want this map P, this projection, to be such that when you actually pull back the anomaly, it's trivial on G tilde. So that's sort of the idea. So you start with your GUV with omega, and you require that the omega trivializes on G tilde, and then basically the center of this G0 with omega can be actually constructed, so from some condensation from G0 tilde. So you have an interface again. Now this could be a high dimensional thing. You can do it in 3 dimensions, 4 dimensions. And then so what the claim is now we can actually do a consistent anomaly matching between this IR symmetry that is now anomaly-free G0 and now dual D-2 form symmetry. So in terms of these sort of RG quiches, essentially we need an algebra in IR such that there's an injective functor, a tensor functor. Now we don't know what a tensor functor is, but we know what conditions on these interfaces should be. So we lift these conditions in the SimTFT to higher dimensions, and we can check that this is in fact a consistent tensor functor formulated in terms of the SimTFT. And one way to sort of think about this is essentially that we're sort of gauging inside this G tilde the abelian symmetry K, get a dual D-2 form symmetry, but it now has, there was the central extension captured by this group cohomology class nu. This is now a mixed anomaly, as sort of discussed long ago by Tachikawa. Okay, so that's just to illustrate. You can then pull this to higher dimensions, do some nice field theory examples as well, and this full formalism works. And it works because we've abstracted it into the SimTFT and then done sort of things that we know are there for these abelian or for these type of symmetries. Okay, okay, and then you can also of course close it up and then play these Wang-Van-Witten games. All right, so okay, so now finished faster than I wanted. Anyway. So we proposed a way to sort of quantify top anomalies for categorical symmetries by saying, well, there's this notion of tensor functors. If you have a UV symmetry and IR symmetry, there's a tensor functor between them that captures the structure that's consistent with all the things you want from the fusion category. But refining this notion to have these kind of short exact sequences, we can then actually quantify which parts of the symmetries are anomaly-free and which ones are sort of really, you can't trivialize them in the IR, so they are really the anomalous building blocks. And these are these ASCIIs. So in terms of the short exact sequences, we translated that into the SimTFT approach. And the nice thing is it's easy to compute with that, and it is generalizable to higher dimensions. And also we can actually include other things. I didn't talk about this, but we also included sort of these sort of LLM type anomalies where you have space-time translation symmetries mixing with... Huh?
LSM.
Yes, LSM anomalies, yes, yes. Thank you. Liebschuls-Matrix type anomalies, yes. I was just saying, why? Yes, thank you, yes. So, but I did say what I meant, translation internal symmetry mixtures, and where you actually take the SimTFT to actually be enriched. So in that case, you take this picture, but you now enrich it with the translation symmetry, and then also can generalize this to some non-verbal examples. What are interesting future questions? Well, one is, can you sort of classify these ASCIIs? So I gave you a small list of ASCIIs at the beginning. So, you know, the Ising category, the anomalous, fully anomalous group symmetries. We had things like Fibonacci, Hagerup, but is there sort of way of classifying them? Those are like our anomalous sort of building blocks. In terms of math, it would be very nice to actually have better notions of tensor functors in higher dimensions for high fusion categories, and to then match that with the SimTFT picture. And then also incorporate sort of things like emergent symmetries that are applied to mixed states, continuous symmetries. So yesterday you heard you can also play this SimTFT game for continuous symmetries. What can we say about anomaly matching in that case? And more generally, space-time symmetry. So this is just one example. You could probably extend this to all those space-time symmetries. Anyway, so thanks very much for your attention.
Any further questions?
Can one classify it if one just considers spec G omega? And if one can, is it then like a classification in terms of group cohomology data? And
yeah, I think in that case, if you just do like G omega, then it becomes this story that I was telling at the beginning. You have a normal subgroup. You have a short exact sequence of groups, And then you need to require basically that n is chosen such that this is sort of the anomaly-free part. Omega is this eco-cycle with this pullback being, so you can probably classify pairs of groups and subgroups that fit into these sequences. So I think that's probably, you essentially just need to check where is this co-cycle non-trivial restricting on, and which subgroup. So I don't think that was not sort of the motivation, because I think in that case we have a pretty good way of quantifying what the anomaly is. It's omega. So what this does is it packages that information now in terms of these different functors. And now the nice thing is you can then apply it to non-invariable things. Yeah.
So the quantification here seems to be like given a fusion category. Like what are these like the ASCs, and then like, what are the possible IR symmetries? That kind of the also.
Yeah. So basically, you give me C, then I construct all sequences where n is chosen maximal. So there's a normal subcategory that's maximal, right? You can also pick something that's smaller, but then this is not accurate, because then S will contain stuff that you could still trivialize in the IR, right? So you really want this to be maximal. And then what it outputs is these projections, SI, and those are the things that you, right, say your symmetry, right, has a collection of these guys, then it says, whatever you do in the IR, you'll see imprints of these.
So the quantity in this quantification would be like that. Exact sequence. And
it's actually these guys here. Probably also you want the maps, but in the end, like I gave you this example of the TYZ4. Once you trivialize the Z2, the gap phases follow the patterns of these ASCIIs. So that's sort of a way of thinking about it, right? You trivialize Z2, so what's left is one of the two ASCIIs, and those they tell you what kind of gap phase you can have.
But for group symmetries,
I know it's a co-cycle, but life is not.
Right.
Life is like that. Categories are more complicated.
Right. But kind of in a general sense, we say we kind of fix the symmetry group, but not the co-cycle, and then we say, well, for this group, what are the possible anomalies?
Yes.
And we get the third cohomology group, right? And then that's like maybe another sense of like quantifying the anomaly.
Yes, right. Do you want to say, could you have a C and now psi goes through different associators?
Right, like, is there a sense where you can fix some part of the
maybe you could, for example? Yes, that's a good question. So you could ask, you have the same object, you have simple objects, but now you have different associators.
Right.
And then which of these are kind of,
right, then like have different labels for those associators.
Okay.
So
yes,
that's like.
For sure, absolutely. That would be a way of really just lifting that to something more of what we know from groups. Yes.
Yeah.
But it seems like,
Can I say there is a problem with that sometimes even the fusion rule by itself it's anomalous.
Yeah.
If you have an object with no integer quantum dimension, it's really
Right,
anomalous.
of course, yeah.
Right. So
But I think there could be cases, right, where you have the same fusion, but you still have some different associators, and then you could ask exactly the complementary question to what you do in groups. And I think then it could be a nice question to ask what kind of ASCIIs are there. Frank?
So how can I understand this just in terms of the bosonization? Like I identify bosons in my fusion category, like self, that basically or self inverses, and I condense them. Is this exactly then the category N?
So
is this equivalent to this picture, basically?
To the picture I just had, so this here, this sequence is equivalent to this picture here. Right? Where was this picture? Yeah, right? So this kind of picture here. So all these little arrows are just saying these are particular interfaces. So the bosons that you're talking about are the anyons that, first of all, there's a symmetry boundary. So there are some lines, some bosonic lines in there, and they give me sort of the lines that braid non-trivially with those generate the symmetry N. Right? And then the same for C and for S. But now there are interfaces. So for example, in the case of the billion group, this was just, I take an interface where I condense 1 e squared e to the 4 e to the 6, right? But then the odd guys basically, right? So this is from here to here, right? So these basically end, and then there's a Z2 that still goes through. There's the E anion that will just pass through, and that generates the Z2 of the Vec Z2. So that's just anion condensation. And then the statement is I want, on the other side, also, in this case it's all algebras, it's condensation. So I want now an algebra that's corresponding to a surjective functor, and that means they need to have the property that basically the only thing that's shared with the symmetry boundary of this algebra is the identity anion. If you go in this example, you basically find, well, the symmetry guy is this one, so the symmetry vector 8. Then there are these two algebras. 1 plus m to the 4, right? So 1 is shared, 1 is shared. But then these are two different algebras. They can condense and get some reduced topological order. And then that again, there's a symmetry boundary here that has bosons. All of these are bosons. I'm only looking at algebras made out of bosons.
But then typically if you condense some bosons, then some other kind of simple objects split actually in other ones. So
yeah, but that's all part of this condensation process. Okay. I mean, because, right, this is just, you have this topological order here, here, and here, and then these kind of, when I specify an algebra here and here, it just means I do the standard condensation of anions. So some of them end, some of them confine, some of them just propagate through, and the ones that propagate through give rise to the symmetries on the two sides. And if I now pick this maximal, so if I pick this algebra here maximal such that I can sort of have this concatenation trivial, then I get these two types of ASCIIs. So it really, in that sense, it's in 2 plus 1, it really is anion condensation. It's just putting it into this sort of picture here.
But so it's always like this, right? Like, I mean, I guess it's always like this, right? Like some inverse of anion condensation. I mean, regardless of what gray, blue, green are, if there's like inverse anion condensation, you go from green to blue.
Well, I don't know, because this is going back to this purple double picture. So all I'm requiring is that this is an topological interface. Yeah. So if I fold it over, I basically just saying there's a gap boundary condition that is, you know, a gap bounding for this double topological order. So now, what I want is sort of an interface. It's a Lagrangian algebra in there, and some of these will come from anion condensation, which means there's an algebra, either a subalgebra here or a subalgebra there, so that it starts off with algebra tensor 1, so those guys all become trivial, right? So this algebra here means I start here and I condense, and they just become the identity anion on the other side. But that's not necessarily always the case. In the examples I showed, it's true, but I don't think that's...
I think there's a theorem that if you take this interface, I don't know, Dimitri, you should comment, but I think if you take this interface, you can always expand it, right, into something where you have a 1 form and a 0 form caging, I believe. But I don't know. No? Okay. He doesn't want to say.
Okay.
All right.
Do you agree with me or you agree with him? Or you disagree?
I agree with her.
I agree with both of you.
Okay. Amazing, but that's not really possible, is it? So I just said I think there can be more general Lagrangian algebras that sit there because, but certainly a good class is when you just do anion condensation. In high dimensions, I don't want to, in fact, restrict myself in any way. It's just saying there should be an interface and it should satisfy certain conditions, right? That we have injective, surjective, and it's a short exact sequence.
Any other questions? Okay, so let's thank Sakura again.
Thank you very much.